I'm Brian Jackson, the I Believe guy and a 3-time world record holder. I hold the Guinness World Record for blowing up a hot water bottle in 51.98 seconds. It can take up to 170 pounds of pressure to blow it up. It's like blowing up 4 car tires. There's actually nothing to stop the air from coming back into my lungs. And it's not just blowing them up, it's being able to hold it to your mouth tight enough that no air leaks. There's been at least 5 people have their lungs explode when they weren't able to hold the air from rushing back in. It's very dangerous. So one of the things I do stress is not to try this at home. Don't go out and buy a hot water bottle and just see if you can blow one up. But when I broke the record, it knocked me out, it dislocated my jaw, and it separated my ribs. It's very dangerous. When the hot water bottle bursts, there's no guarantee where it's going to go. Sometimes it bursts in a couple of pieces, and sometimes it bursts in hundreds of pieces. It's like somebody punching you.
Hi there. To start today's presentation, Dean will be outlining what a synthetic jet is. Seamus will explain how they work. Josh will be discussing the applications of synthetic jets. I'm Ryan, and I will inform you of some of the benefits and limitations of synthetic jets. And finally, Curtis will give a brief overview of the podcast.
Synthetic jets are formed by moving air in and out of a small orifice, as shown in this video. The diaphragm oscillates up and down, and a periodic airflow is produced. Air moves in and out of the cavity hundreds of times per second. It is ejected from the orifice at a high velocity, and then sucked back in at a lower velocity. The result is a jet of air that is synthesized entirely from the ambient fluid.
By alternating the current between positive and negative values, the piezoelectric disc oscillates. The cavity and diaphragm are designed to maximize the amplitude of the oscillations. By operating the diaphragm at its natural frequency, it is possible to optimize efficiency. The synthetic jet is a simple design with no moving parts. This makes it a good alternative to large fans, which can be noisy and difficult to maintain. A synthetic jet is created by inserting a piezoelectric disc into a resonance chamber with an orifice at one end of the chamber. An alternating current is applied which causes the disc to oscillate up and down. As a result, air is pushed in and out of the orifice at a pre-select pulsating frequency.
Synjet airflows produce a train of vortices. These are formed entirely from the working fluid flow system, which means they can add momentum to the flow they are injected into, without changing the total mass. The flow is ejected from the orifice due to the diaphragm oscillating at a certain frequency, which causes the flow to be pushed out then sucked in. As the flow is pushed out, it typically separates at the edge of the orifice, and a vortex sheet is formed. This rolls into an isolated vortex that is propelled away under its own self-induced velocity.
The primary pulses of air are ejected from the orifice at high velocity, which causes a secondary airflow to be generated. This happens because of entrainment, where the surrounding ambient air is pulled in by the primary high momentum pulse. The two airflows mix together to form a much larger airflow than the small volume of air that was initially ejected from the cavity. This short video shows what is happening. Notice how the stagnant air is entrained behind the primary pulse. to form a much larger airflow. So, we have provided you with a brief summary of how a Synjet works. The key point to remember is that momentum is added to the airflow by sucking in a small amount of air and pushing that air back out at a higher velocity. This means the synthetic jet has a net mass flux of 0. It is a simple and energy efficient method for adding momentum to a larger body of air.
As today's electronics generate more heat inside ever small spaces, engineers are challenged to find new ways to effectively cool components. Using synthetic jets as an air cooling technology can provide a high local heat transfer coefficient at a much lower flow rate, which increases reliability and energy efficiency. For LED lighting, it is vital to keep temperatures as low as possible, as 85% of their power usage is lost as heat. Using synthetic jets for cooling LED lighting can increase their lifespan, as they will be operating at much lower temperatures. This is shown on the graph.
The performance of an airplane wing has a significant impact on issues such as runway distance, approach speed, climb rate, payload capacity and fuel efficiency. One main contributor to the performance of the wing is flow separation. Various active flow controls such as vortex generators have been used to delay flow separation. However, they induce a drag penalty when the flow is not already separating. The benefit of using a synthetic jet to delay flow separation is that it does not induce a drag penalty. Researchers found that synthetic jets enhance the lift by up to 7% for low Reynolds numbers and increase the limiting angles of attack by up to 6 degrees in some cases, as the jet delays flow separation. Synthetic jets can also be used to provide virtual shaping of aerofoils with the possibility of replacing slats and flaps in the future. For example, Synjets can be used to alter the direction of the flow and apparent local shape of the aerofoil to increase the lift achieved without changing the angle of attack. The flow separates from an aerofoil when the momentum becomes too low, so by adding more momentum to the flow it remains attached. This delayed flow separation is achieved by the synthetic jet ejecting vortices. These vortices stabilize the airflow by adding momentum to the boundary layer.
Synjet cooling can reduce heat sink size and therefore the weight without sacrificing thermal performance. Because a synthetic jet is an active cooling solution, the thermal performance of heat sinks are better than similar size heat sinks cooled by natural convection. This allows greater design freedom, which is critical for LED consumer products. One disadvantage, however, is that moving components like pistons or diaphragms complicate both manufacturing and assembly, as they are delicate and easily damaged. Despite the benefits shown in the comparison chart, synthetic jets are a new technology with limited research.
Okay, so I'm just going to talk about the benefits and limitations of synthetic jets in terms of aerodynamic application. The wing is at a high angle of attack, and as you can see, the airflow is currently separated. As the synthetic jets are switched on, the airflow then reattaches to the wing. Synthetic jets are applied to the upper surface of an aircraft's wing with the purpose of improving lift and delaying stall at high angles of attack. Additional advantages in aircraft application include saving weight, as well as the operation being simple and energy efficient. However, synthetic jets do have their limitations. Similar to electrical applications, synthetic jets for airfoils are a relatively new technology with limited research. In terms of manufacturability, the manufacturing and assembly is complex, where the moving devices are often delicate and easily damaged, with a limited lifespan. There is a decision to be made between electromagnetic and piezoelectric drivers. Electromagnetic drivers are used to move pistons, which are generally large and heavy, whereas piezoelectric drivers are much smaller and lighter. This is why they are preferred in both electrical and aerodynamic applications. The trade-off between the two devices is that piezoelectric drivers produce smaller and less powerful bursts of air, adding less momentum to the main flow compared to that of the equivalent electromagnetic device. Okay, so in summary, here are the main benefits and limitations for electrical and aerodynamic applications. Okay, so you sat through our presentation, but what are the main conclusions that we would like you to take away from our research on synthetic jets? A synthetic jet is formed by ejecting and sucking fluid through an orifice such that the net mass flux equals zero. It's a relatively simple concept which can be related to how we breathe or a bike pump. The main advantages, particularly for electronics and aerospace, are that it saves space and weight. One of the major drawbacks that we have found is that this is a relatively new technology and requires further research. It should be stated that only two main applications have briefly been examined within our podcast: electrical and aircraft. However, in terms of aerodynamics, synjets have a potential to enhance efficiency in a wide variety of applications, such as windmills, turbines, and the fan blades in turbomachinery, to name just a few. So that concludes the end of our video. Thank you for listening, and we hope you have learned something today.